Hi guys, welcome to Cycloalkanes. I built a model of cyclohexane, but I made it flat. We're going to talk about that later. It's not actually flat, but just for purposes of being able to see the relationship of the groups. This is very similar to double bonds in that there's a fixed rotation. I can't just rotate this any way that I want. So if I have two methyl groups, I'm using oxygen as an example because I ran out of carbons, but if you have two methyl groups, let's say here and here, then the side view would look like this. You would be looking at it on from the side and you'll see the two methyl groups pointing down. So that's what this side view picture is about. And these little wedges here are just demonstrating that they're pointing toward you, these carbons up here. Okay, top-down view would be just draw cyclohexane, and these methyls are in the back. You could also have rotated it this way and have the two methyls wedged toward you. Okay, either one is correct. Now I'm holding the trans version. Trans means across, so the two methyl groups are across each other from this plane. All right, if we were to think of cyclohexane as a plane, one's on top and one's on bottom. So that's shown with this side view drawing. And then top down view is just rotate this like that, because we usually draw cyclohexane like this on the paper. One is in front and one is in the back. So use a wedge and use a dash. And for now it doesn't matter which one you wedge or dash, but later we'll learn about stereoisomers, and it will, a little more about stereoisomers, and then it will matter. So these two structures are considered stereoisomers and not just conformational, because you cannot rotate the cis or trans into the other. So if I try to rotate this, because of the ring, it's acting like my double bond before, where I couldn't rotate or twist it around. So there is no full rotation I can do of any kind that will get both of these on the same side as each other. They're just always going to have to be on opposite sides. So I would simply say there's no rotation possible to interconvert between the two isomers as we can with the conformational isomers. On the next one, it's just getting used to thinking about the groups on the ring. This is on cycloalkanes, so they're all cyclic. And there's two groups that we usually compare on the ring. So we have a bromine group or bromo group and a methyl group. And notice they're both wedged, meaning they're both pointing out at you. So would this be cis or trans? Cis is same side. In fact, remember we use Z for cis. So this is Z or cis. And I'm using cis when there's only two groups to compare. Why don't you guys try the rest of these? And remember, there's also a possibility of neither cis nor trans. So take a careful look at these. Some of these are neither. All right, guys, we're back. Neither is when you have the same groups attached. So I have methyl pointing up, but who do I compare it to? They're the same here. So this is neither. If I switch these groups, I have the same molecule. Here I have trans, one on top, one on bottom. Here I have top and bottom, but who am I comparing it to? These are all hydrogens, so there's neither. I can switch any of these hydrogens and it's the same molecule. I could switch these two groups and it's the same molecule. And then here, top, bottom, trans. So now let's draw trans 1,4-dimethyl cyclopentane. I'm going to use the template over here. So I'm going to start numbering 1, 2, 3, 4, and 1,4-dimethyl. And I want trans, so think about that. Do I want to use both wedges, both dashes, or one of each? I'm going to use one of each for trans. They're on opposite sides. Now, I made a mistake in naming this. Did you guys catch my mistake? What's wrong with this being trans 1,4-dimethyl cyclopentane? Well, when we number, we usually number so that there's the lowest number of branches, right? So I should say this is a 1,3, not a 1,4. Now we're going to look at different size rings. I'm going to build cyclobutane. That's 4 carbons in a ring. And I'm going to look down the carbon-carbon bond as if it were a Newman projection with the disk right here. And do you guys see the relationship of, you see the conformation, is it eclipsed or staggered? All right, here's the side view. Side view, do you guys see that it's actually eclipsed? Okay, that means that the clouds are really repelling each other due to torsional strain. So what the cyclobutane molecule will do is try to bend a little bit out of the plane so that you can see that now they're not quite so eclipsed. Okay, so now you can see they're a little bit more off from each other, askew. All right, so that is how the molecule will try to minimize the repulsions. So it will adopt a kind of conformation where it's twisted, if that's possible. Now let's try, and then let's also look at the bond angle. Okay, so with cyclobutane, it's pretty hard to get away from being close to a right angle because it's forced into a square. And if you think about 90 degrees there, and what is tetrahedral carbon like to be for bond angle? It prefers to be 109.5. So we're quite a bit away from 109.5. And that makes this molecule a little unhappy, okay, uncomfortable. Now let's try cyclopentane. Now when I build cyclopentane to be flat, you can see by sighting down the bond, okay, there is a bit of eclipse going on there, right? So you see alignment between these hydrogens. So again, try to twist this molecule. And there is a way to get almost staggered. Okay, so we are twisting this, and there's a way to get somewhat staggered. You can see that there. So this molecule will flip and rotate and fold onto itself, sort of like an envelope, okay? And that's how it will try to avoid that strain from the nearby hydrogens. Now we talked a little bit about that deviation from the ideal bond angle. So if you look at cyclobutane again, 90 degrees, cyclopentane on paper looks like 108, and cyclohexane on paper looks like 120. But it turns out that actually of these, you have a pretty good bond angle here. Even though it looks like 120 on paper, it actually is 109, very close to 109.5. And the reason why it's not 120 is, again, because of the folding. That allows my atoms to have a better bond angle. So for example here, okay, looks like 120. All right, and this is planar. But as I fold the molecule into its conformations, it's able to adopt its preferred lowest energy form, which we call the chair. And I'm going to show you how to make a chair later. But there's a preferred folding of this molecule that allows it to have lower energy. And in that conformation, cyclohexane is able to maintain its tetrahedral character. So the deviation that each molecule might have, you know, how much it is different from its ideal bond angle. So if it's closer to 90 degrees, but it prefers to be 109.5, that additional strain of being less than the ideal creates a strain energy. So for cyclopropane, which we didn't build, cyclopropane is 3 carbons in a ring like this. And so you can imagine the greater bond angle deviation there from ideal. So this is going to have the highest strain energy. 4 carbons, you still have a lot of strain energy, and you see it start to decrease towards 6 carbons. And that's really the best you can get, is with 6 carbons. That's really ideal. It's just the right size, not too big, not too small, to allow carbon to have its tetrahedral character. And then as you get bigger, you have more degrees of freedom. The molecule can start folding on itself in ways that are not as favorable. So looking at these data, it makes sense with building the models, because the cyclohexane can actually be completely staggered all the way around the ring. So here's a a view of that. If you look down this carbon at this carbon, you see this is up, this is gauche, this is down, this is anti, okay? So you can have that all the way around the ring. So there is a very stable conformation for 6 carbons in a ring. So cyclohexane has the least deviation based on its strain energy. Alright guys, so to get that stable conformation, which we call a chair, I start with the planar cyclohexane, so everything's flat here, everything looks symmetrical, okay, and all the hydrogens are eclipsed. Alright, so everything's eclipsed going around, and it's completely flat. Then I take one corner of it, so these are opposite corners right here where my fingers are. I'm going to fold this upward or toward you, and I'm going to fold this downward toward me. And by introducing that fold, you now have all the hydrogens staggered. Alright, so make sure that I got that. So see, if you look through this bond, you see up, side, side, down. Okay, that's my staggered. You see that for all these right here. Alright, so staggered all the way around, and what the ring looks like is it's pointed upward here, then it goes down, then it goes up, then it goes down. There's a kind of zigzag to it. Let me show you on paper. Down, up, down, up. Okay, so that's representing the zigzag carbons in this conformation. We call it a chair because if you put it sideways and rest it on a table, it looks like a chair that somebody can come and sit inside right here. Okay, it's hard to see without a model, but it really does sort of look like a chair this way. Okay, alright, so there are different positions around the ring. We have axial that are pointing straight up or straight down, and equatorial are the ones around the ring going sideways. Alright, so I've now replaced all my axial hydrogens with green, and you can see they're pointing straight up or straight down, and the white here, these are equatorial because they are pointing sideways or sort of across the horizon, kind of. Alright, so on this we've got A for axial, so these are axial positions, and then the lines going sideways, these are equatorial. I do want you to be able to draw every group on the ring going around, so I want you to be able to know, how to draw those up, draw these down, and draw these sideways just the right way, because it really matters whether you're pointing them slightly up or slightly down for these equatorial positions, or whether the axial is pointing up or down. So I have a special exercise on that I'll show you later. So let's use this template to identify if these hydrogens or carbons, whatever you want to call them, if these groups off the ring are axial or equatorial. So this one here matches this one. So this is what we call equatorial, and you could probably see that it's not straight up or down. So it's equatorial, and this is what we would call equatorial up. This is axial, and it's pointing down. Why don't you guys try the rest of these and tell me also, is it pointing up or pointing down? Alright, one thing that might have helped is if I told you that every position, every carbon has one group up and one group down. So if it's easy to see axial up or down, then you use that to say, oh, if this is axial down, this is equatorial up. Okay, axial up, equatorial down. So when we look at these, we see axial up, we see equatorial, and if it's hard to see if it's up or down, it looks like it's going down though. But if you look over here, we have an axial up, so we have an equatorial down. Over here, equatorial down, equatorial up, axial down, equatorial up. Now the reason why I like to use up or down is because that tells me about cis and trans. These are up and down, so this is trans. This is up and down, so this is trans. This is down and up, this is trans. This is down and up, that's trans. If they were both up or both down, that would be cis. So that's how you can tell in this kind of chair conformation which groups are cis or trans to each other. Let's build cis 1,3-dimethyl cyclohexane, and then let's draw it over here. Alright guys, I removed some of my hydrogens and things just so you can see the methyl groups are cis to each other. I have them in my chair conformation, so the zigzag, okay, such that these two groups are axial, they're pointing straight up. So yes, they can be axial. If I try to make them equatorial, all right, and then maintain my zigzag, all right, I can get a form where they're both equatorial. So here's my axial down, equatorial up. So they're still both up and up, so they're still cis to each other. So yes, I can rotate the bonds and make them equatorial in a way that maintains their cis to each other. But if I make one axial and the other equatorial, they're still going to be up and up, but it's not the chair form anymore. So I can't quite get them to maintain that zigzag I had before, the chair conformation. If I try to maintain that, they can either be this way or they have to be this way. So they have to either be both axial or both equatorial. So if I made one of these, let's use our template to see this more clearly. If I made one of these axial and one of these equatorial and maintaining my 1, 2, 3, they're 1, 3 dimethyl, if that one was axial and one was equatorial, then I'd have an up and a down, so that would be trans. Okay, that couldn't be cis. So they either have to both be axial in this 1, 3 position, or they have to both be equatorial in order to maintain their cis relationship. So that gets us into something where we rotate the bonds and we can flip the chair. Now when I say chair flip, I don't mean taking this chair and flipping it. That's not really what we mean by flip. What we mean is we take this chair and we rotate the bonds so that all the groups are flipped or changed in some way. So if we have a methyl group down here and we do a chair flip, notice that it's axial right now, axial down. When I take this corner, which is sort of pointing down a little, this V right here is pointing downward, and this V up here is pointing upward. That's this V right here. So I usually keep my eye on those guys. When I take those and I take this down V and I move it up, and I take the up V and I move it down, then I get what we call a chair flip. And notice what happened to my methyl group. It's now closer to you, okay, so or farther away if I want to rotate it this way. And the methyl group is pointing downward and it's equatorial. So axial down going to equatorial down. So notice though that the thing that stayed the same, even though axial was going to equatorial, the down is still the same. It's still pointing downward. So that means I'm going to be able to maintain cis and trans. If it was cis, it's going to stay cis even after the flip. If it's trans, it's going to stay trans after the flip. So I have a very cool animation that I want to show you of this chair flipping. Alright guys, if you Google or if you YouTube search chair cyclohexane chair conformation animation, you will find this. I think it's very cool. So it's showing you one of the chair conformations. Here's my V pointing down, and then these two lines and a V pointing upward. And notice all my blue hydrogens here are axial. So now as this thing, it's got energy, it's constantly rotating and changing conformation. It went through something we called a half chair, where this part becomes planar, and this part is still a V sticking up. So it's a half chair in that this part came up a bit. And then it came up all the way, and you can see that we have eclipsed hydrogens now. So we're increasing our energy. This is a more, a less stable conformation, higher energy. All right, and then so it twists out of the plane in order to try to make more space for those hydrogens so they don't repel each other so much. So we get something called the twist boat. So it twists out of the eclipsed, and then you get the boat, which really didn't last there very long because it's so unstable. Notice we have eclipsed hydrogens. These are eclipsed, and these two groups repel each other because they're on the same side. So it's going to quickly get out of that by twisting again, trying to get these farther apart. And then into the half chair, and then into the chair finally. All right, and there we go. Nice even chair, axial straight up and down. You can see those in red. Now remember at the beginning we had blue up here, and we had red over here, equatorial. Now they're switched. So my V is going up here and down here. Before it was down here and up here. So what we did was we took this corner, flipped it up, took this corner, flipped it down, okay? And so we have everything in the opposite. So we've got our axial blue turned into equatorial blue, equatorial red turned into axial red. So back to this, let's fill this out. I want you to show for carbon 1, this axial, which is black here, it becomes equatorial. And the white is equatorial, and it becomes axial after the chair flip. And notice my V right here, it's now pointing up. Okay, so go around the ring, and also notice this V is up, and now it's pointing down. So go around the ring, and go ahead and fill in each of those groups. So what you see is the methyl group that started in the axial position becomes equatorial. So I'm just going to fill that in right now. And then I drew all my equatorial white hydrogens in the axial positions, and after the flip, the black axial hydrogens became equatorial. All right, so let's look at carbon 1 here has an axial methyl group going down. So what happens after the flip? Here's my carbon 1. So I took this V and I flipped it up. Where should the methyl be? Up or down? Well, it's down before, so it stays down. So it's got to be here, and this happens to be equatorial. So axial turns into equatorial, but down stays down. Here we have carbon 2, methyl group going down, equatorial. Here it's going to be down, but it's going to be axial. And these guys, you have to write hydrogen, otherwise we assume it's carbon. Finally, the last part of this is we've got different conformations now. Now that we can do a chair flip, we can have one form where the methyl groups are axial to each other and one form where they're equatorial to each other. So now we have to think about which conformation is lower energy. And this is like our Newman projection, eclipsed and staggered, except these are all staggered because they're chair conformations. Everything's staggered around the ring. But we want to consider that when groups are axial, they can have a closer spatial relationship than when they're equatorial. You can see here that the equatorial groups are pointed away from the ring. So if I were to imagine their electron clouds, these axial ones have clouds that are very close to each other, creating repulsions. We call those 1,3 diaxial interactions, and that's considered a type of steric repulsion. Okay, so that term might be new to you. Steric repulsions referring to groups that are close together, similar to our eclipsing strain from before. So now we have these methyl groups. They're farther away, so they're not interfering as much with the hydrogens that are in here. Let's take a look at those hydrogens. We've got axial hydrogens here, here, and here, and axial hydrogens here, here, and here. So you can see they're going to have their electron clouds, and they're sort of out of the way. They repel with each other, okay? So you're still going to get some kind of repulsion, but it's not going to be as bad as with the methyl groups, which are bigger and bulkier and will really get in that space and repel more. Over here, let's draw in our axial groups. We've got axial hydrogens here, here, and here. All right, so 1, 2, 3, 1, 2, 3, or 1, 2, 3, 1, 2, 3. So every other position has an axial. And when we draw those electron clouds, you see they're really close to each other. So I would prefer to have this conformation because it's got less steric repulsion, or only the hydrogens are repelling, whereas here we have this large methyl group. So maybe I should show it like that. So we have a lot more repulsion here. So I'd like you guys to do this practice, and we'll compare answers later or check the answer key, and if I can, I'll try to make a video on it. All right, good luck everybody.